So this is the class on computer systems analysis. Very first class, and we will be spending time on telling you about what we are going to do in the rest of the year, rest of the semester. So 5 parts of this first lecture. What is this course about? What are we going to cover? On what time frame? And a project. Some of you have taken my previous graduate courses. Exactly same format. We have a project and grading. So the goals of this course, basically I have designed it to be the most comprehensive course I can think about performance analysis. I started out as a performance analyst myself at Digital Equipment Corporation long time ago. And one thing I found that the things that we used at the company were not taught at the school. And the things that were taught at the school were not really used at the company. So there was a big mismatch. So I sat down and wrote a whole book on what is important. The book is called The Art of Computer Systems Performance Analysis, and that is the textbook for this course. And the book is actually won the best computer systems award from someplace. I think Computer Press Association. So it has been a very famous classic book, and it is 20, I don't know how many years, 1991, 21 years old, but it still sells very well. Anyway, so the reason I said all this is because I want to make sure that you understand that this course is different in that we try to concentrate on what is important out in the real world. And throughout this course, you will hear those kinds of things as to how to really do the things for the real world and not just for writing a paper. So this includes 3 parts or 4 or 5 parts actually. It turns out that most of the courses that are taught on performance analysis, they either just talk about queuing theory and we're done with it. Queuing theory is the only analysis method that they know. Or they will just talk about simulation. And if they're very hands-on people, then they will talk about measurement. But there are very few courses. I haven't seen any courses on measurement. And the word experimental design, nobody in the performance analysis community had heard about until we brought it out. And so this course actually covers all those 5 parts: measurement, statistical modeling, experimental design, simulation, and queuing theory. Now that is a lot. That's a lot, and we will have to do that with joint effort. And you will have to do some reading, and it's a very easy to read book. If you have gotten the book, you can read it and you will see that. And then some here. How to avoid common mistakes in performance analysis. So there are some things that I noticed during my career as a performance analyst in the industry, and I want to make sure that we avoid them, and we will talk about that. That is the next lecture actually, right after this. And since this is a graduate course, it's advanced topics. There's a lot of independent reading and writing, and in particular there is a survey paper you have to write in addition to the exam. So the project or the survey paper will talk about that. That really teaches you how to know about the latest things which are not in the books. Because most of the things today are not in the books. Believe it or not, by the time you write the books, they are 3 years old, and by the time the things are already used, out of date. So now more than ever, it is important that we be able to research things online and learn fast. All right, the internet has made several things easy, and one of them made it easy is writing papers. But reading is not very easy. Reading is still you have to do manually, and writing and publishing is very easy. So we got to read. Book we already talked about, Art of Computer Systems. Has anybody tried to get the book? Did you find it locally or? Amazon, okay. All right, but I gave the order to the bookstore here, and they might have some copies for those of you who need the copies locally. Objectives. So what will you learn? You will learn how to specify performance requirements. And that is the first thing. If you are designing a product, or if you are, I mean, in the research world, probably you don't start there, but in the real world, first thing you have to do is set up the requirement that this computer I am designing, or this database system I am designing, or this, whatever I am implementing will be twice as fast as this competition. Right? And so how do you specify the requirements? Then you will have to sit down and write down what my alternatives are, and then compare those. And so we'll teach you how to compare 2 or more systems. And when you have a system, there are parameters, there are things that you can change, so how to tune them. And find the performance bottleneck. And that is one of the key things I will teach, or I want to emphasize throughout this course, is that the bottleneck is the key. If you want to improve the performance of anything, first thing you need to find out what is the bottleneck and work on the bottleneck. Because if you make the bottleneck twice as fast, trust me, your performance will go twice as fast. That's it, period. No more mathematics required. If you work on anything else, you can make it 100 times faster, but the performance will not go by 1%, may not go by 1%. Because the bottleneck is still the bottleneck. All right? So the first thing is the bottleneck. Characterizing the load on the system. So first thing is, what is the real workload to use? And so if you are going to use any simulations, if you are going to do any analysis, if you are going to do any measurement, you need the right workload, because otherwise it is garbage in and what? Garbage out. So if your input is just out of the air, you could as well take the output out of the air. Right? So it's important that we take the right workload. Determining the number and sizes of components in capacity planning. So in some places, if you are particularly in an organization where you have to purchase things, you have to worry about how fast things to purchase. Obviously, money is in short supply, regardless of where you are, whether you work for a bank or International Monetary Fund. You need to worry about getting the right sized computers, or right sized equipment, because you cannot just say, well, get this fastest thing. I mean, everybody cannot afford Ferrari. They have to find the right car that can work for their budget. Right? Predicting the performance at future loads, and then forecasting. So all of these things will be covered. Now, before I go more into detail, there are 3 terms that I will be using very often, and you have to understand those, so I'm going to explain those. First is system. Now, when I say a system, it could be any little thing, or it could be any big thing. It could be any collection of hardware, software, firmware, anything. So for example, if you are just writing a search algorithm, that's your system. If you are designing a database system, that's your system. If you are writing a software for some sensor network, that's your system. So the system is something that you are studying. All right? So don't think about the system as being bigger than something. Obviously, there are things outside your system, and they affect the performance, and you have to worry about them. But things that are in your control, that is the one. Metrics. We'll use the word metric. Metric is how you compare, how do you measure the performance? How do you characterize the performance? So for example, for a computer, you might want to say, well, I want to see how fast some particular program runs. That will be your metric, that it runs in 2 seconds. Another computer runs in 3 seconds. Or how fast the response comes back for the user, or how many transactions can it do, 200 transactions a second, or how many searches can it do. So depending upon the system, you have to select the right metric. Workloads. Again, we talked about the workload. Workload is the input that basically goes into the system so that you can put it to the right load. So the request made by the users of the system. So we'll use the word system, metrics, and workloads. Now, this will become even more clearer as we go to each chapter. There is a whole chapter on metric, there is a whole chapter on workload, and there is actually a part of a chapter defining the system. All right, so there are 6 parts of this course. Part 1 is just the overview that we will do mostly today. Second part is measurement techniques and tools. So that is how you measure the performance. Third part is probability theory and statistics. So there we talk about lots of random numbers. Fourth part is experimental design and analysis, and actually there is a slide on each of these in the next few slides. So I'm not going to go through that. I will go through them as we come. Experimental design and analysis. Fifth is simulation, and sixth is queuing theory. So performance evaluation. We talk about actually the whole introduction that we are doing right now. Then we talk about common mistakes and how to avoid them. So I made a list of over 50 mistakes that I have noticed people made, and I wrote them down, and we can probably add to the list. But basically we'll talk about those, and then selection of techniques and metrics. So the first thing we'll talk about is what technique out of all these 4 or 5 techniques we're talking about. Should we use statistical modeling, should we use measurement, should we use simulation or queuing theory? Those are actually 3 alternatives: queuing theory, simulation. Actually, queuing theory and statistical modeling probably go together. So we generally call modeling. So modeling, simulation, and measurement. 3 techniques. And metrics. What performance criteria we will use. So here's the first example. What performance metrics should you use to compare the performance of the following systems? 2 disk drives, 2 transaction processing systems, and 2 packet transmission algorithms. So all of you know about the disk drives. Let's just ask you, and you tell me, if you were to compare 2 disk drives, you're just in the market to buy a disk drive. How will you choose one? Given that the rest of the other things are similar, like in this, the common, if you are looking for a 500 gigabyte, you're looking at 2 500 gigabyte drives, right? So how will you select? Anyone?
Times to read and write data. Times to read and write data.
Read and write speed. So that's your metric is how many megabits per second, how many megabits or bytes per second, and read and write speed. Right. Good one, yeah.
The energy requirement.
And he is worried about the green, so he will say how many watts per minute or hour, how many watts does it use, basically, not per minute. Okay. Anybody else? All right. What about how often does it break? Don't you go and read the reviews on Amazon before you buy it? Because that is not in the seller's specifications. It doesn't say that it breaks every 3 months. Right? How do you find that out? By going and seeing how many people have given 1 star, what percentage of people have given 1 star, because those are people who just found it really not working. Right? So reliability. So there are many other metrics that we need along with what we call quote performance metric. And so a complete characterization of quote performance of that system has to include such things as reliability. Right? Otherwise you will end up with a product which is very fast but doesn't work. What good is that? Right? I mean, it came with 500 gigabyte per second, but it worked for 1 day. And so your boss will fire you the next day. And so, all right, so that's the kind of thing. So we will have a whole chart, flow chart, which says how do you find the right set of metrics. Second part is measurement techniques and tools. Here we will talk about lots of stuff here, but actually there is a lot of things on the list here, but most of these are in the book. We may not be able to talk in the class about all of these, but let me just go through the list here, and they're easy to read. First is what are the different types of workloads. So there is a dry stone, there is spec, there are many different kinds of workloads you may have heard about. If not, you will hear about. And why should one use this or that? Popular benchmarks, and these are some of the names that I mentioned a minute ago are popular ones. The art of workload selection. how do you select the right workload, how do you characterize the workload. So basically one of the things that you may have to do is to measure the workload. Say if you are working for Facebook, I mean there is no workload that is known beforehand. You have to measure it on the real system today and then use it for tomorrow. All right. And if you are working for a bank, maybe there is a system that some other bank had already measured, so you can just use a standard thing there because those things are very standard. So like that, you have to do characterization. It means you have to measure the workload and somehow characterize it. Say, well, this is what the workload looks like. Monitors, which is basically part of measurement. Accounting logs. And those actually turn out to be the most easiest way to get the workload. Is you go to the Facebook accounting and see what people have done, how often, and how often they make a new friend, how often they do this, how often they do that, and then you get a workload. Monitoring distributed systems. That's basically a problem because every system, one system is here, one is over there. How do you coordinate and all that? Load drivers. And then last problem is in the measurement is that you really have to drive a system with thousands of users. So let's say you're designing a system for Facebook. They have millions of users. Maybe a billion, I don't know. So the idea is we are given a lab, performance analysis lab. You are in charge of performance analysis. And now you have to drive this system where you find 1 million or 1,000 or even 100 users. How do you do? Any idea?
Maybe other computer can generate it?
Yeah, exactly. So the thing is, so we do a load driver, which means that we set up a system which looks like 100 users, 1,000 users. You put a number 1,000, it's a big system. It can produce 1,000 random commands of different types that you have programmed in the workload. So so basically we wrote lots of remote terminal emulators in my days. And so those are the load drivers. Capacity planning we already talked about, and then the art of data presentation. Now the main thing is that your analysis doesn't stop at the measurement or modeling. You have to present it, and if you didn't present it right in the industry, it is useless, totally useless, because it's your waste of your time and waste of their money to hire you if you didn't present it right. Because you have to present it so that they can understand. And finally, the ratio games. So how do you show your performance? Game. I use the word game here in the sense that how do you? In a lot of papers you will see that they present the performance of the system looks much better than the other guy. All right, but if you just change little bit, same data, just change the way you analyze it, and it turns out that they are worse than the other guy. Right, so I noticed lots of such games in some very respected papers, and so I have a chapter on that. So example, which type of monitor, software monitor or hardware monitor? So here monitor doesn't mean a display. A monitor means a measurement thing, right? Software monitor, hardware monitor would be more suitable for measuring each of the following quantities. So you want to measure the number of instructions executed by a processor. What will you use? Hardware monitor or software monitor?
Hardware.
Huh?
Hardware.
Hardware. Why?
I don't think that the software will scale.
Yeah, the speed at which things are happening, right? Degree of multiprogramming on a time-sharing system. And by the way, let me just say before, the question for the grading is coming up. But some of you have taken the course before, so you know that the more you answer, the more you question, you get grades. All right? So please try to answer. Even if it is wrong, it doesn't matter. And I want you to interact. I want this communication to be bidirectional, not unidirectional overhead transmission. So, so raise your hand, answer the question. And the more you do, because at the end then you'll say, sir, I didn't get this mark. Well, sorry, I never saw you raising a hand. So that's just a mental note I'm making. Degree of multiprogramming and a time sharing system. What will you use? Everybody knows what is the degree of multiprogramming? No? Nobody knows what is the degree of multiprogramming? Okay, maybe times have changed. Do you know what is degree of multiprogramming?
It's the number of programs running.
Yeah. Okay, number of processes running on the system. So what do they call it? I mean, if that should be kind of obvious for the computer science people. Is there another name for it?
Number of processes.
Okay, well, here's the thing. Maybe I am a little bit out of date on this, but in our days we had just started multiprogramming, time sharing. Before that there was no time sharing. You run then your program, one program, and that's it, done. If you wanted to run two programs, there was no way. Well, actually it was before my time, but anyway, so the thing is, when they started running two programs, and this was called multics, by the way. Multics is multiprogramming, for multiprogramming and all that. And so that was a invention, and one of the important things, how do you do multiprogramming? How do you do, and multics, and then after that came Unix. Unix is actually named after multics. It's a copy of multics. So multics, Unix is play on multics. And Unix is very popular. It is a multiprogramming system, but I don't remember now what U stands for. Maybe it is universal or whatever it is. But basically, it took all the technology that was developed at MIT and multics and then put into the real world. All right. So done that. So multiprogram. How do you measure the number of processes running on the system? You want to know whether there are 300. I mean, basically, generally on a real system, you are not really measuring the number of processes. You might be more interested, rather than this, number of users on the system. Right? So how do you measure that? Hardware or software? Yeah.
Software.
Huh?
Software.
Why?
It's countable.
Yeah, it's probably not easy to do it by hardware. The hardware memory doesn't know. I mean, the CPU probably can count, but it will be software, right? I mean, that's good. And then I'm not going to go through the response time of packets. Okay. Probability theory and statistics. Now, this course is on performance analysis and modeling. So that is one thing I want to warn you. There is a lot of statistics here. I'm not assuming that you know a lot about statistics, but if you have never heard of a random number, you will have difficulty, because this cannot be your first course. Generally, that level of statistics is taught in the high schools, I assume. And so I will tell you in the next slide, actually this slide itself has some of those things, as to what are the things you need to know. And that might be a showstopper, in the sense that if you don't know, then in spite of everything else, you may have to wait until you have taken one course in something. All right. So probability and statistics. So 4 important distributions. If I say normal, uniform, you have to know what normal is, what uniform is. All right. Summarizing major data by a single number. So when you get 1,000 numbers, or you get a whole sheet full of numbers, you measure the number of users, and for a day you will get 1,000,000 numbers. You're not going to present to the management and say, look, I measured it and here is the list. They're not going to look at the list. They don't need the list. What they need is one number. How do you do that? How do you do that? Summarizing variability of the measured data. So you say, well, the average is 64. So how good is that number? Could it be 64,000? The answer is yes. Then 64 makes no sense to me. Right? Can it be 100? No, sorry, it is very close to 64. Then yeah, this is a good number. And so we have to worry about how variable that number is. Graphical methods to determine distributions of measured data. And often you have to say, well, this thing is normally distributed, this thing is exponentially distributed. That was the third distribution, which is very common. This thing is, whatever it is. So how do you find out whether it is distributed like that? So you have to do the distribution. And we will teach you how to do that. Sample statistics, confidence intervals, So confidence intervals we will teach again here in the class. Comparing two alternatives will teach you how to compare two different things when, again, there is a lot of variability in both systems. Measures of relationship. So how do you know whether this thing is related to that thing? Like if you increase the number of users, something changes. Maybe response time goes up or down. So what is the relationship between the two? Simple linear regression model. So straight line fitting. All of you know straight line fitting. Probably they teach you in high school again how to fit a straight line. That is called regression. But we teach you all over again in this course. For two reasons. First of all, we teach you so that you do it statistically correctly. Second thing, there are lots of concepts about testing your models, checking your models, that I find it very easy to explain with regression, and then we use them throughout the rest of the course. Multiple linear regression models and other regression models. So here is an example. So by the way, all this list here was, you really don't need to know, in the sense that this is what we will teach. So we will teach you 4 important distributions, how to measure the data by single number. This is all in this course. But if you have never heard of a random number, that would be very difficult for you to understand any of this. Right? So here is the example. The number of packets lost on 2 links was measured for 4 file sizes. So we took a file of size 1000, and let's call it 1000 megabyte or 1000. Nowadays, in my days it used to be kilobyte. Now it is 1000 megabyte. Or actually, it already says packets. So 1000 packets. We sent 1000 packets, and on the link A, 5 were dropped or lost. On link B, 10 were lost. All right, that is our first workload. Second workload, 1200 packet file was sent, and 7 were lost on link A and 3 were lost on link B, and so on and so forth. Which system is better? I'm sorry, can you say loudly a little bit?
For a bigger file size, link B is better. For a small size, link A is better.
Link B is better for big file size, 1300 it is not. Oh, better, it is better actually, last. Okay, 3 is better, 3 is better, 10 is not good. So you're saying 1000 maybe, okay, that's, okay, so that's a good observation. That is one of the observations, but there are other ways to say this thing, and we will explain to you, teach you exactly how to say, and then justify your answer. So the biggest thing is, in the real world is, it's not what you say, but how you justify it. There could always be a different answer, because that's why my book is called The Art. It's not a science. Everybody sees, the beauty is in the eye of the beholder. So the answer is in the eye of the beholder. What is the right answer is in the mind of the person who is telling the answer. And we may not agree, but if you can justify that this is why I think this is right, that's most important. If you yourself have no idea, then obviously you cannot sell it. Right? So you have to know how to find the right answer your way, and then do it. All right, part 4. Part 4 is experimental design. Now, what is experimental design? I don't know of any other performance analysis book in computer science which talks about performance experimental design. However, we introduced it in 91, and now there are lots of papers I can show you which use this. And most of the projects that we had done in this class in the past, they used experimental design. And most of the projects that I taught at other places before this university, they use experimental design. And the reason is, here is the problem with the experimentation. What is an experiment? First of all, if you are doing a simulation, you have to run 1,000 different cases, because the parameters are different. So you have to see the effect of the parameters, different parameters. So that is, each simulation is an experiment. If you are doing a measurement, you have to probably do at least tons of measurement. You cannot do 1,000, but at least you can do hundreds. So each of those is an experiment. And just like there is always shortage of money, there is always shortage of time. So ideally, you would like to do 2 million experiments, but obviously they don't have money and they don't have time to, you don't have time to do it. And therefore, you have to find what is the minimum number of experiments that I can do. So will answer come out, well, you can do maybe 15 experiments and then you will get most of the answers. So that is one part of the experimental design, is to find the minimum number of experiments that will give you the answer. Second part is which 15. Now there are 1,000 possibilities, so you have to find the right 15. Third thing is, if you find the right 15, how do you analyze it? How do you get that information that you're looking for? So that is called experimental design and analysis. Okay? So all of these words here will be totally foreign to you today. So don't worry. Basically, we'll teach you what is a 2 raised to k factorial design, what is 2 raised to kr factorial design with replication, 2 raised to k minus p fractional factorial design, what is 1 factor experiment, what is 2 factor full factorial design, and so on. All of this is new stuff. I don't think you have learned that in the high school. So this is something that you have to wait. So here's an example. Performance of a system depends upon following 3 factors. Garbage collection technique. Anybody knows what is garbage collection? Some people know. Okay. So basically, when you use the memory and the program goes away, the memory has to be somehow collected back. And generally, the systems will wait for a time. Just like in our offices, they don't collect garbage every second. They collect in the evening. So there has to be a garbage collection cycle in the computers when they collect all the memory, put it back into for use. All right, so we have three techniques, G1, G2 or no technique. Type of workload could be editing, computing or artificial intelligence. Type of CPU, C1, C2 or C3. So there are 3 factors and 3 possibilities. How many experiments are needed? Well, one answer would be we need 3 times 3 times 3, 27 experiments. All possible combinations. But if I just increase the number 3 to something large, right now it is 3 raised to 3, I could give you 10 factors and 10 experiments, 10 possibilities each, that would be 10 raised to 10. And then what? And not only that, you have to measure it, you have to analyze it, so to figure out whether it is the CPU which is causing the problem, is the workload which is important, or is it the garbage collection technique which is making a difference. If you are designing the garbage collection techniques, you are not even going to think about any of the other things and say, well, wait a minute, my technique is the one that really does everything. All this performance is because of that. And that may be true or may not be true. It could be the workload. That you selected a workload that is good for your system. Just like she said that it was good for the big packets. So maybe it was the thing that you just didn't use the small packets. Right? Okay. So simulation. So it turns out in research in particular and in the advanced product design in the industry as well, most of the time that thing that you are going to measure is not there at all. So the computer, the database system, the algorithm, thing that you are designing is not there. It's just in your brain. And so what do? You have to do simulation. So simulation is the most common technique used in the life cycle that we are in, most of us are in. Some places you can do measurement, but those places are very limited. Some places you can do queuing theory, but that is only for the professors. Most people cannot do that. And so really simulation turns out to be the main thing. And so we will teach you about the simulation. What are the different types of simulation? How do you verify and validate the simulation? And these are two different words, verify and validate, and we'll talk about that. Analysis of simulation results. And just like workload affects the performance, another thing that affects the performance of simulation is random number generation. If you have a wrong or bad random number generator, your results will be wrong. So that is the key. So we talk about testing random number generations, and then random variate generations. What is the number and what is a variate? Number is basically what happens when you want to generate a random number is you generate a uniformly distributed number, and that is called a random number. And then if you need a normal, you do something with it and you get a normal distributed number. That is called a variate. So anything which is not uniform is called a variate. And commonly used distributions. And then we talk about some of the common things like exponential and Bible and so on and so forth. We will not talk about those in the class, of course. They are talked about in the book. But it is important that you read that part so that when the time comes, you know some of the things that are in that chapter. Yeah.
Can you explain again what is a variate?
Okay. So we use the term variate for those random quantities that have a distribution other than uniform. If it is uniform, then we call it, you said, we call it random number. Okay. If the thing that I generated like this, that is a random thing, right? But if we generate many of these and if it is uniformly distributed, then we call it random number. And all in the simulation, most of the time we just generate the random number first, which means we generate a uniform number first. Okay? And then we do some calculation on it, like take exponent of it, or take a log of it, or do something to get other distributions from the same thing. So the key is the random number generator. Random number generator gives you a uniform number. So here's an example. In order to compare the performance of two cache replacement algorithms. So here is one more thing, let me just say throughout this course. There is a lot of statistics, but this is different than the statistics course. Because if you go to statistics course, they don't know about computers, and their algorithms would be, their examples would be very boring in that sense, for you, right? Here, this is designed for computer science. We have no other examples. We don't take examples from medical field. We don't take examples from agricultural field. We don't take examples from any other field. Everything is computer science, and this is what we have used. Most of the things that we are here, actually, I have in the book. I have two kinds of things: examples and case studies. Case study is the real thing, in the sense that somebody did that in the real world. Every number is real. Every problem is real. Examples are something that I made up. Okay, so that is the difference about this, is that we have tried to apply these techniques to the real computer systems, and we have come into the issues that other people may not have come into, and we have resolved them. And so that's what we are going to teach about. Is so the reason that thought came to my mind is because it says cache replacement algorithm, and you could do simulation of many different things, but here everything is about computer systems. So what is a cache? Good, perfect. So before you put into the memory, which is kind of you have to get it from the disk or some place. So actually the other way around, is that if you have to go to the memory, it might be slower. So you put into the cache. It is much faster memory. And the thing is, it's faster, it's expensive, and therefore it's small. And so it's quite possible that it becomes full very soon and you have to replace some of this stuff to put the new stuff. Everything has a cache. Even disks have a cache. When you read the disk, you don't want to go to the disk every time. You read it beforehand, put it into the cache, and when the cache becomes full, you throw out some stuff, older stuff, put the new stuff in. So the question is, what type of simulation model should we use? And right now we didn't even talk about what are different kinds, so I will not go into the answer. How long should the simulation be run? And that's another thing, is that you run the simulation, so do you run it for a day or a half day or 1 hour or 30 minutes? That's a very important question. I can read a paper and I can tell you that this guy didn't run the simulation long enough. And we will teach you those techniques. That's why it is called the art. And so that is, and we will tell you how to really find the right length. So that is another thing. What can be done to get the same accuracy with a shorter run? How can we decide the random number generator is a good generator? So all that. All right, the final part, queuing theory, and actually an important part. So we will talk about what is queuing theory, how do you analyze the queue. By the way, why we have to worry about queuing theory in computer systems? Does anybody know what is the queues of? What are the queues of? Yeah? Jobs. Yeah. If you have processes running, you have 100 processes running, they are standing in a queue. Right? And you decide which one to be serving first. This is similar to, when you go to a supermarket or a bank and you have to decide how many queues to have and which things to be put in what queue and how to take them out. So all that is, so there is lots of queues. Every single resource in the computer has a queue. The disk has a queue, the memory has a queue, the CPU has a queue. If you have a network, it has a queue. And so the whole performance is queuing theory. So queuing networks, then something called operational laws, and that is what I really want to teach, because operational laws is what we call back of the napkin calculations. Most of the courses in queuing theory, they teach you a very deep queuing theory stuff, some of the things that I even cannot read without going crazy with so much equations. But really in the real world, what works is something that you can explain to your boss on the back of the napkin. All right? And there are techniques that will give you that kind of information. And so that's what I want to explain. Operational laws. Mean value analysis, that goes a little bit more mathematical, convolution theory, and advanced techniques. So we will probably not get that far, but this is all in the book. We will probably get up to operational laws, and if time permits, an MVA, mean value analysis. Here is the example. The average response time of database system is 3 seconds. So you did the measurement and you found out that your database system takes 3 seconds to answer the query. You ask, what is my balance? And it tells you in 3 seconds. During 1 minute observation interval, the idle time on the system was 10 seconds. And then you observed it for 1 minute, 60 seconds. Out of that, it was busy for how long? 50. And 10 it was idle. That's all you know. Now, can you tell me what is the system utilization? What is the average service time per query? What is the number of query completed during those 50 during that minute? Average number of jobs that were in the queue in the system. What is the probability of the jobs system being more than 10? What is the 90 percentile response time? What is the 90 percentile waiting time? All of these things. Can you tell? The answer is yes, under certain assumptions. What are those assumptions? So we'll talk about that. Then the art part more. Actually, you saw throughout this course, you saw notice so far, everything is art, in the sense that people think that performance analysis is mathematics. And in mathematics, there is no two answers. 1 plus 1 is 2 always. All right? But it is not. I mean, obviously 1 plus 1 will always be 2, but I mean the performance analysis, there will be situations where the answer will be very different for the same data, for the same system, for the same everything. Here's an example. Throughputs of two systems A and B in transactions per second is as follows. A with the workload 1 gives me 20, B gives me 10. And higher is better. On workload 2, A gives me 10 and the B gives me 20. Now I work for company A. What do? I want to show that my system is better.
The only way you could ethically say that system A is better is workload 1 is what your customers are actually using. If your customer is using workload 2, then B has to use it.
So one thing is that you forget workload 2, just hide it in the rugs and say, look, workload 1 is the one which is most common and I have measured it and this is most important. So most paper when you read, this is what they do. First they justify the workload in the sense that they will say small jobs are the most common and then we are optimizing performance for small jobs. Right? But if your system doesn't work for small jobs, then you say, no. The big jobs are the most important one and here is the performance for the big jobs. Right? So that is one. Okay. Any other technique? Okay. So it turns out there are several ways to do this. One is that we want to use both the workloads. First of all, the rule of the game is that somehow somebody has said that I want you to compare the performance on these two workloads. Your customer has told you already. So you cannot hide it under the rug. So one way you could say, well, that look, we measured performance on both workloads and we took our system as a base. We are number one. We have one here and they have only 50% of our system performance. They have, actually this would be company B. If they wanted to sell themselves, they would say, look, we took the ratio with A as the base and we are half as fast, but on workload 2 we are twice as fast. On the average we are 1.25 times better, 25% better. Is this okay? What is wrong? Go ahead. Yeah.
Well, is two workloads are enough to measure to decide?
Is it two?
Yeah, I mean we only see two workloads.
Yeah.
1 and 2, but is it enough to say according to only 2 that A is better? Sorry, B is better?
Oh, okay. So you're saying the number of workload is not big enough. If it was 11, maybe there won't be any problem.
Maybe.
Okay. Anybody else? Yeah.
When you're averaging ratios like this, you're supposed to use the geometric mean.
You're getting there. Okay. Anything else? All right. So here is the thing. When we go to this chapter, we will show you real results from real professors from real universities, published papers in the most respected journals where people use this technique with a large number of workloads, like 11. And it was just basically used, this is the kind of thing they used. All right. And one could not figure it out that this data can be done the other way around until you work it out the other way around. So other way around is that if you are working for company A, what you will do is you will just take the ratio other way around. You will say we will take B as the base and just do that. You will take B as the base. I think it was right here in the previous slide. B as the base and they will be 25% better. All right. So that's so much about what we will cover. Any question about what we will cover or not cover? There is a lot, yeah.
Since you have the ability in some sense to skew the data, Is there a definitive way to determine one system is better than another?
We'll talk about that. That's why we have comparing two systems and other things. And as I said again, is that you have to, so there is a recommended way. Again, is that you have to work out yourself 5 different ways so that the other guy cannot raise finger and say, well, you did it wrong. Because the answer will come out different. I mean, which base you take here in this case, base A or base B. And you publish a paper and you say, I took the base B, then they will come back and say, look, I did the same thing with base A and the answer is different. So you have to work out both ways. If they are different, then you have to do something different to figure out which is the right way to go, right? And sometimes it is not, and then you have to, that's where the art part comes in. Is there a definite way to decide the color of a painting? None. You try out 3 different colors, maybe some color looks better. Not painting, but product design. And so, so the thing is, yeah.
So isn't this art?
This is what?
Isn't this example like art as well?
Art?
It's like art, right?
Art. Yeah. Art, yeah. So the thing is, as I said before, this is the art part, is that, scientifically, one could argue either way. And this is exactly, I keep telling you, is that whatever you say, you have to have a reason as to why you are saying it. And then somebody comes up with a different way of doing it, then you say, all right, I didn't think about that, or maybe let's work out these differences. Or the best thing is to do all those different ways beforehand. So you're on a solid ground. All right? Okay. All right, grading. So we have 3 exams in this course, just like every other course I teach. A midterm and a final, but there are 2 midterms. And the reason we have 2 midterms is because some people can get sick, some people may have to travel, and so on and so forth. If you cannot make one, you are allowed to take the second. If you can make one, you are allowed to take the second. All right? There is no third makeup exam. Period. You cannot get sick both days. You cannot get travel both days. In the final, there is not even enough time to give you a second exam. So final, there is only one final. So we take the best of the first 2 plus the second. The first 2 count 30%. The final counts 30%. So total is 60%. Then class participation is 5%. So everyone who is asking question, answering question, and as I said, it is not important that the answer be right. It's important that you participate, that you talk, that you speak, that you do something, because in the real world, you go to a meeting, company meeting, if you don't speak, they don't know that you are very smart. The smartness is measured by the output, right? So anybody who speaks, even if they are dumb, like they say, this guy is a loud chatter, whatever it is, they get promotions and raises and everything else, and you, very smart guy, kept quiet. So there it is that, and that is not the reason here. One more reason is that I really want to get the feedback. Without your answering the question, I don't know what level I should be at. Right? And it's also good training for your future. So that is 5 points, and that is totally up to me. That is the only point that I have myself in my control. Rest of the 95% is in your control. You cannot question me how I gave the 5 points, but as I said, I have taught many classes here. People have taken previous classes and they know that I am very fair on that one, but I don't change. So the rest is 15% on the homework. We will be homework in every class, and you will have to turn in the homework on Monday. So if I give you a homework today, it will be due next Monday, which is a holiday, so it will be due on next Wednesday for that reason. And here is our TA, teaching assistant. He will grade it, and you will get 15% of the total, of the grades based upon that. his detail is coming up in a minute. Excuse me. And then there is this paper we talked about, that is 20%. So that makes up the 100%, and everything is into pieces. Like homeworks will consist of, I don't know, if there are 28 classes, maybe 25 homeworks, and project, even though it is one project, but there are several steps along the way that we will grade. The real thing is at the end, though. So the first few steps are kind of not that highly, valuable, but they're important. And what else? Let me see. There are something. Oh, okay. So let me go to the next slide, maybe. Okay. Well, any questions about grading? Nobody wants 5%?
Can the project that we use here be our senior thesis? So if you're like, can the project that we use here, like, can we use it as our senior thesis, or use it as our?
Can we use
this project, like the paper, as our thesis?
Thesis, of course. So the thing is, that's a good question. Most people will use this opportunity to use the techniques that we have taught in this course to apply to things that they are already doing. If you are working on something, that is the right thing to apply the techniques to. All right? And I'm all for it that you apply it to your thesis. You don't have to do extra work just for this course. It will be good for you for both, because what will happen is then you will really think about what is the right answer, right thing, right technique, if you are working on a real problem. If you are working on a made up problem, the answer will be made up. Okay? So if you are working on a PhD thesis, master's thesis, anything, or you are just developing anyway, writing a paper, use these techniques and submit that technique part to this class, and your whole thesis might be 500 pages. I don't care, I am not going to read that. But for this we have 15 pages, and I need 15 pages to be concentrating on the part that is in this course. And let me say this, most of the projects that have been done in this class were like that, or many of the projects, let me put it this way. And many of the people, many of the masters and PhD theses in this university, I have seen using the techniques that they learned in this class. And that's my goal, basically. My goal is so that you use it in the real world. And right now your real world is your thesis. Once you get out, I don't even know, but hopefully, you will use it. Any other question? All right, prerequisites. So first of all, I need everybody to know computer science. So if I use the word cache, multiprogramming, things like that, I hope that you have heard it before, because I'm not going to explain. I don't have time to explain, computer science here, in some sense, taken the right way. So actually, this is a computer science course, but this is not. We are not talking about operating systems or databases, something that you will just take examples from those areas, even networking. Then, if you have done some programming, that would be good, because we will ask you to do some calculations. And we used to write programs in our early days, but nowadays there is Excel, Microsoft Excel, which does all the computation you never need to do. So get good book on Excel, or good online thing on Excel. Make sure that you know it so that you can do it very fast. So I really don't care how you got the answer. I mean, basically, I care how you got the answer, but what tool did you use? Whether you used a calculator, whether you used a slide rule, or whether you used a C program, that's, same thing for me. As long as basically, if you wrote the C program, you wrote the right answer. If you use Excel worksheet, you wrote the right formulas, things like that, right? So you need an introduction to computer programming for that reason. You need to be able to write some things. Introduction to digital logic, and we don't require that. This is not a hardware course, and we don't basically, we don't worry about it. Basic probability and statistics we need. All right. So if you have never heard of random number, as I said before, don't know what a mean is, what a variance is, that is going to be tough. Matrix multiplication and inversion. There are many places where you have to multiply the matrix. You have to know how to multiply the matrix, how to invert a matrix, how to take a transpose of a matrix. This is a course on analysis, right? There is a lot of math here. So, those are the things. So, here are the things that you should know. Mean and variance. What is a normal distribution? What is a density function? What is a distribution function? What is coefficient of variation, correlation coefficient? What is a mean, mode, quantile? These things you need to know. So if somebody said, well, I have 90 percentile or 80 percentile and 95 percentile, what does that mean? Right? If I say median of 100 numbers is so and so, you need to know that. All right. Anybody has a question about prerequisite? And so we will cover all this according to this schedule, not according to this schedule, try to, because I never know what I will be teaching, but this is based upon the last year's schedule. So I know I can do it, and I have taught it 100 times by now, I don't know how many times. I have taught it at MIT, I have taught it at Berkeley, I have taught it at Ohio State, I have taught it here, I have taught it in India, everywhere. I wrote the book, so obviously. So I kind of know how long it takes. By the way, I just taught at Berkeley last semester. I was on sabbatical at Berkeley. So, and the book started at MIT 1981, 82, 83, 84, 85. That's where the book, after teaching the course, I wrote the book. So, anyway, so the idea is, this is the rough idea. The exam, the most important thing is that the exam date is fixed. February 18th, 2013, please mark it on your calendar. That will not change. If you have any appointment on that day, make sure that it is adjusted accordingly. You cannot say that I have to go for this interview on that day. Well, that's your decision. You can go because you have a second exam coming up. And whatever we have covered by that time will be in that exam. So if we don't cover regression, it won't be there. If we cover something else, that will be there. Right? So these things, everything in the black is changeable and may change most likely, but the red is fixed. Second exam is on 325. Again, mark it on your calendar. It would be good if you take both exams. You get 2 chances to improve the grade. If you take one, it's okay. And there is a break in between. So these dates are fixed. The final exam is on 4/24. Notice that it is not in the final exam period. It is actually the last class. Yeah.
Will that be a cumulative final or just?
Is it a cumulative final? Yeah. So I have actually decided not to take cumulative anything. So everything is incremental. For the exam part, so the second exam only covers the material covered since the first exam. The third exam only covers the material from the second exam. However, having said that, in real ways it is cumulative, because if you don't know the first part, you cannot do the second part. If you don't know the second part, you cannot do the third part. So I will not ask you explicitly in the exam about things in the first part, but they will be used anyway. Yeah.
From this list of chapters, can we conclude that we will make this whole book?
So the answer is yes and no, because there are some chapters that we just put in the list, but they are not. For example, the book ends at chapter 36, I think. Here only ends up to 34. 35, 36 we will not cover. There are chapters in the middle, in the beginning, if you notice them. It doesn't go either way. Let's see where does it go. In the beginning, there are chapter 5, 6, 7. Some chapters are missing there. So, I mean, I cannot, because there are not 36 classes for 36 chapters. When I wrote the book, I wrote it so that one chapter a day you can finish. That was the idea. But since there are only 23, 24 classes, we do only 23, 24 chapters. But we cover the whole book in the sense that those chapters that we are not covering in the class, we are covering in the home. I mean, you can just read them. Except the last two, which obviously you won't get to, because if you need to, you can read it yourself. Okay, any question about the content? None. We go to projects. So it has to be a paper which could be of many different kinds. For example, it could be a survey paper, it could be a case study, it could be whatever. I mean, we will lot more example will give you. You could do a survey paper on some workloads of different types, measurement, modeling, simulation tools, survey on some particular area of the computer science. Performance analysis based. It's not that you want to write a paper on sensor networks here. In this class, you write performance of sensor networks, performance of databases, or something like that. It could be real case study, and that is what I would prefer, that you do a real case study on a system that you are already working on. And I expect that you will spend about 6 hours on the project, 9 hours on the class, total 15 hours. And anything that you do here has to be new. Last 2 to 4 years. I don't want anything that is more than 4 years old, anything that is in the books. Wow, what's happening? How can that happen? You have a remote control? Can you turn on the light again, please? Michael, turn on the light again. All right, so not in the books, and if you write a good paper, we can submit it to a journal, to magazine, to or whatever, or a conference, and that has been done in many cases. Although in most cases it is people just publish it with their advisor rather than with me, so that's fine with me, that's not a problem, but basically that's the goal, is something that is new. Everything goes on my website. Every paper that has been written in this class and any other class is on my website. A lot of people read it outside, a lot of people submit it to their course advice, course classes outside. A lot of people have published it as a paper with their name on it. But I mean, we try to get hold of as many cases as possible, but obviously we don't have time for all of that. But basically the point is that we don't get to be caught. We don't want somebody to catch us and say, well, look, this is a copy of our thing. Okay? So the goal is to provide an insight or information not obvious before the project. And that's the goal. And the real problems such as thesis or job, if you're working for a company, you have some problem to solve, fine, take that problem. And the homeworks are basically to apply techniques learned in your class, right? Examples of previous case studies. So this is the exact correct list. This is the list from the last year. Okay? And so obviously you cannot do this. You cannot do this here because we don't want to repeat. If you have to repeat a project here, then let me know so we can think about as to how your angle is different. But here is an example, and you can see Google App Engine, Amazon Web Service, Smart Grid, hypervisors, virtualizations, image sensors. So this is somebody's thesis, things like that. And this is the list from previous year. This is a list from all previous year and so on and so forth. You have the whole handout. You can go to the website. You can read these papers. The papers are all online, and you can read them.
These are just located on your website?
Yeah, if you go to the course website this year, there is a pointer which says the previous offering of this course are available. So I think we did it in 2011, before that 2008, 2006. You just click on those years, you will get 2011, and you will see all the papers. 2008, you will get all the papers. 2006, you will get all the papers. In fact, you will get all the course handouts and the recording. So you don't have, you can even listen to this lecture as I gave in 2011. I'm recording everything. This will be on the website. This will be on YouTube. And anybody can listen. Everybody listens. Lots of people listen. Okay? If you miss a class, you can listen to the class, exact class as it is, or you could listen to the previous class, previous year's class. All right. Schedule. So the dates are February 25th you start. On that day you should have selected the topic by that date. A week later you have to give me the literature list, papers that you have found on the topic. Hopefully you have done all that beforehand. Before you selected the topic, you have found the papers, because you are selecting the topic, I am not. So I mean, you have done the work beforehand that, okay, I like this topic, I have found enough papers, I can do it. So if by chance you haven't done it, here is the guidance though. I mean, like, I will just explain to you before, a few days before that, what are the hot topics nowadays? What are people interested in? So for example, when people selected Google App Engine and things like that, how did they come to that smart grid? Because those are the hot topics right now. All right. So I will give you some idea of the areas that are really good and interesting. Cloud computing, right now is very hot. And so things like that, and then you go into that area if it is interest to you, and then select a topic yourself, do the literature search, and within a week that is due. And then you give me an outline 2 weeks later. An outline is simply, these are the things that I will discuss in my paper, so kind of headings. And then the first draft is due on April 3rd. And this is the final actually. A lot of people think it is a draft and this and that, and that's a misnomer. This is the final thing you're doing. This is like you submit to a journal. You cannot be submitting half-done job to a journal. So the final paper is due on 4/3. The only thing is that we do get it reviewed by the peers. Everybody will review 3 papers, so you will get 3 reviews of your paper. Just like a journal. You get 3 reviews, then you change your paper and submit the other one in 417. So you cannot write a new paper in 417, because now it needs to be reviewed if you change the whole thing. It's just the minor changes. So you will be graded mostly on this one, 4/3. In fact, every reviewer will give you a grade. Again, it's not in my hand, it's in your hand. Is that clear? And since the dates are fixed and firm, make sure you make your schedule to be ahead of the schedule. All right. My office hours right now are 11 a.m. to 12 noon on Mondays and Wednesdays. And here is Michael. Michael is visible. And he is in 405G. Email is given. And I am not sure whether the hours are still good. 2 to 3 on Tuesdays, Thursdays.
Yeah, Thursday, Friday will work well, 2 to 3.
Thursday, Friday. Is that what I wrote? Yeah.
Thursday, Friday.
Yeah, Thursday, Friday, sorry. Thursday, Friday. Yeah, okay. So that makes up 4 of the 5 days of the week. Basically, I am Monday, Wednesday, he's Thursday, Friday. So if you need the help, hopefully you will get the help. So few more details about the course. I do use a curve. My curve is simple, very simple. Is that if there are 18 people in the class, 9 will get something better than A minus or A minus, and 9 will get something below A minus, which is B plus or below. We cannot give more than 50% A's. And so there is no particular number I can say, well, if you get 67, you get an A. That is not there. Whatever is the median, halfway, then we divide into A minus, A's, and A plus. Below we divide B plus, B minus, C plus, C minus, D plus, C plus, whatever. And the ranges are constant, so basically there is no playing around here that I want to give somebody an A plus. So that way it does depend, your performance depends upon the rest of the class. If everybody is smart, 50% still get a B. All right, because there are some people who are smarter in some sense by some metric. And 50%. Of course, if everybody gets within very small amount, then I'm a statistician and I know that difference doesn't make a difference. I mean, we treat you about comparing systems, right? Don't we? So the whole thing about this grade has come from this course. How to compare students. And so if there is no statistical difference, obviously, we will have to be breaking that rule of, giving 50%. If 100% get, within 67, 68 or something like that, there is no statistical difference. But that doesn't happen. It doesn't happen in any course that I have taught, and this is the thing I use in every course. So 50% A's, and A's means A minuses and up. Any late submission will always have penalty, and any thing is, whatever valid reason you have for lateness, sorry to say this thing, you could have a very, very valid reason that I cannot submit it on time. You submit it before, but if you could not submit it before, not submit it on time, there has to be a penalty. The penalty depends upon the how late you are and how important it was for you to submit late. Okay, I mean, if you are going for a very valid reason, I will give you a very small penalty. If you are going for some not valid reason, you will get a larger penalty. So submit it on time. The exam is closed book, and so the book is not allowed, but you are allowed a cheat sheet. You can bring 8.5 by 11 cheat sheet, a piece of paper on which you can write in microprint, whatever size you want, print it out, type it out, write by hand, whatever you want to do, you can bring that sheet. Okay? And time is limited though. The whole thing is that, basically the exam day, you will have a limited time, and so if I don't limit the time, if I give you infinite time, then obviously all the grades will be equal, and then, we won't be able to distinguish. Exams consist of numerical as well as multiple choice questions. So there is negative grading on incorrect multiple choice questions. So multiple choice have a problem in the sense that if I give you 2 choices and you randomly mark one, 50% chance it will be right, 50% chance it will be wrong, and so for the wrong answer you get -1, for the right answer you get +1, and so on the average you get a 0. Right? By randomly thinking. But if you have some idea of the answer, if you have 10% sure that this is the thing, you will get 10% chance of getting 0.1. I mean, basically you will have 10% chance of getting 1. So don't randomly answer. If you have little bit bias towards 1, then take the chance. And similarly, if I give you 3 choices, 1, 2, 3, A, B, C, and you randomly mark, you have 1/3 chance of getting it right. So if you get it right, you get +1. If you get it wrong, you get -1/2. 1 upon n minus 1. Okay. Everyone, including graduating, and I don't consider anything else as a parameter. Your color, your sex, your gender, or your nationality, nothing else, including whether you are a senior or a junior or graduating this year. I don't control any of that, and I don't control everything comes in the computers. Your exam, he grades it, and that's it, done. Your home survey paper, your peers grade it, that's it, done. Okay, so don't come to me, sir, I got to graduate this. If I don't get this one, I won't graduate. Well, I'm sorry. There's nothing in my hand except those 5 points, and those are not done by me, those are done by you itself. So you cannot just come last minute and say, sir, this and that. That's the end.